Lagrange multipliers are a handy way for finding maximum and minimum values of a function under a constraint condition. Sometimes this is called a method of constrained optimization. Let's start by looking at an example. We want to find the rectangle of largest area that can be inscribed in the ellipse with this equation. Let me draw the ellipse. It looks something like this. And we want to consider inscribed rectangles whose sides are parallel to the x and y axes. So a rectangle might look something like this. And we want to find such a rectangle with maximum possible area. As we're considering various inscribed rectangles, a nice way to keep track of which rectangle we're talking about is by specifying the coordinates of the upper right corner, which I'll call coordinates x, y. Now the area of my rectangle will be the base times the height, so that's going to be 2x times 2y, or 4xy. That's the function that I want to maximize. I'll call it f of xy equals 4xy. But because the rectangle is required to be inscribed in the ellipse, x and y are constrained to lie on the curve given by this equation. So if I let g of xy equal x squared over 4 plus y squared over 9, then my constraint condition is that g of xy has to equal 1, so that the point will lie on this curve. Let's look at the problem graphically. This blue surface is the graph of z equals 4xy. So we want to find the maximum z value on this blue surface. But we're also subject to the constraint that we need to lie on the magenta surface given by this equation. So we want the highest point on the blue surface that's also on the magenta surface. One of those points is right there. Now let's look at a two-dimensional picture of the same thing. In this picture, the light blue curves represent the level curves of our function f. That is, the curves of constant height for our blue surface. And the magenta ellipse, that's our original ellipse. In other words, it's the graph of g of xy equals 1, our constraint condition in 2 dimensions. Now when I look at this picture, I immediately think of taking a hike. The magenta curve is like my trail projected onto the xy plane, and the blue curves are like the contour lines of my mountain. So the maximization question is asking me, where on my trail will I reach the highest point on my hike? Not the highest point on the entire mountain, that might be way over here somewhere if there even is a maximum. But I'm just looking for the maximum constrained to walking on this trail. Please pause the video for a moment and think about where that highest point on the trail might be. Could it be, for example, right here or right here? I claim the highest point on the trail could not be at this point right here, because at this point the trail crosses a contour line. So by continuing on the trail in one direction, you have to go higher, and the other direction you have to go lower. By picking the higher direction, you're guaranteed to find a higher point on the trail, so this cannot be the maximum height point on the trail. Even this point here, even though it doesn't have a contoured line drawn through it, it seems plausible from the location of the other contour lines that there is going to be a contour line that crosses the trail here. So it's not plausible that this could be the highest point on the trail. So the only way a point on the trail could be the highest point is if there's no contour line, no level curve crossing through it. In other words, the level curve at that point has to be tangent to the trail. It looks to me like a point right here might have a level curve tangent to it. So that point right here is likely to be a highest or lowest point on the trail. So the key idea here is that the max and min points on the constraint curve can only occur where the level curves of f are tangent to the constraint curve. g of xy equals 1. But the constraint curve is itself a level curve of the constraint function g of xy, since it's where g of xy has height 1. Therefore, we need to find points where the level curves of f and g are tangent to each other. Since the level curves of f are perpendicular to the gradient of f, and the level curves of g are perpendicular to the gradient of g, we're looking for places where the gradient of f and the gradient of g are parallel to each other. So we want the gradient of f to be parallel to the gradient of g, or in other words, the gradient of f should be a multiple of the gradient of g for some number lambda. If we look at all these candidate points on the level curve, together with the places where gradient of f or gradient of g don't exist, or are 0, then we'll find all the candidate points where the maximum or minimum point on the trail might be. This is the theory behind Lagrange multipliers. Written out in more technical language, the theory of Lagrange multipliers is as follows. To find the maximum and minimum values of a function f of xy, subject to the constraint g of xy equals k for some number k, assuming that these values, extreme values, exist and that the gradient of g is not 0 on the constraint curve, we need to, first of all, find all points x0, y0 such that the gradient of f is parallel to the gradient of g, that is, where the gradient of f is a constant multiple of the gradient of g, and compare the size of our function at all these candidate points. In practice, we set up the following equations. First, we need that f sub x is equal to lambda g sub x. Second, that f sub y is equal to lambda of g sub y. This is just unpacking the equation that the gradient of f is equal to lambda times the gradient of g, since the gradient of f is the vector with components f sub x, f sub y, and the gradient of g is the vector with components g sub x, g sub y. Since we're only interested in points with this property on the constraint curve, we also need to use the third equation that gives the constraint condition. So in practice, we write down these three equations and then solve this system of equations for x, y, and lambda. In the end, we don't really care what lambda is, but the values of x and y that solve the equations, we can then plug into f and compare the size to find maximum and minimum values. For this method to work, the constraint function g must be smooth in the sense of having continuous first partials. Otherwise, we must also check any cusps or corners on our constraint curve g, where g sub x or g sub y don't exist or have discontinuities. Let's get back to our original example. Remember that our maximization function for area was 4xy, where x and y represent the coordinates of the upper right corner of our rectangle. And our constraint condition was given by g of xy equals 1, where g of xy is x squared over 4 plus y squared over 9. We need to set up the three equations. So let's find f sub x, that's 4y, f sub y, that's 4x, g sub x, that's 2x over 4, or x over 2, and g sub y, which is 2y over 9. Our three equations are now 4y equals lambda times x over 2, 4x is lambda times 2y over 9, and x squared over 4 plus y squared over 9 equals 1. There are many different ways to solve systems of equations like this. One way is to solve for lambda in the first two equations, being careful to consider separately the case when we've divided by 0. Now, setting lambdas equal to each other, we get 8y over x equals 18x over y, or x equals 0 or y equals 0. This equation simplifies to y squared equals 9/4 x squared. And if I now plug back into my third equation, I get that x squared over 4 plus 9/4 x squared over 9 is equal to 1. That simplifies to x squared over 4 plus x squared over 4 equals 1. So x squared over 2 is 1. So x squared is 2, and x is plus or minus the square root of 2. Plugging back into equation 3 again and doing some minor arithmetic gives us that y squared is equal to 9/2. So y is plus or minus 3 over square root of 2. This gives us 4 possible candidate points where the gradient of f and the gradient of g are parallel on the constraint curve. And those candidate points are square root of 2, 3 over square root of 2, minus square root of 2, 3 over square root of 2, square root of 2 minus 3 over square root of 2, and minus square root of 2, minus 3 over square root of 2. Since our original problem had to do with a rectangle whose upper right corner was in the first quadrant, the candidate points with negative x or y coordinates don't make sense. So that remains our candidate point for the maximum value. Now we sort of ignored this extra special case where x is 0 or y is 0. So let's make sure we consider that possibility. Notice that if x is 0, then looking at the first equation, y also has to be 0. And similarly, if y is 0, then looking at the second equation, we know that x is 0. But we can't have both x and y be 0 because that violates the third equation. So in fact, this is not a possibility. And the square root of 2, 3 over the square root of 2, is our only candidate point for the maximum area. To finish the problem, I'd like to find that area, and we can do that by plugging our candidate point into our function f that we're trying to maximize. So the area is going to be 4 times the square root of 2 times 3 over the square root of 2. That's an area of 12 units. In this video, we developed Lagrange multipliers. The key idea behind Lagrange multipliers is if we want to maximize or minimize a function f subject to a constraint given by a function g, then we need to look for where the level curves of f are tangent to the constraint curve g. This happens when the gradient of f is a constant multiple of the gradient of g.